Hey guys, it's Mr. Sala here. Today we're going to talk about Unit 0, which is Chemical Foundations. This unit is going to be what you talked about in 10th grade chemistry, whether it's advanced, on-ramps, or on-level. Okay, so most of this you've already seen. There's only going to be 2 new topics, which I'll talk about when we get to them. But you've seen these before. If you don't remember all of it, that's okay. This is why we have this unit. We're going to talk about it. If you have questions, you can ask me in class. But all of this you've seen before. So starting off with some vocabulary, we have isotope, mass spectrometry. Those two will go together. Empirical formula and molecular formula. Electron configuration and orbital diagram. We have the periodic trend, so ionization energy, electronegativity, and atomic radius. Covalent network solids, VSEPR, and stoichiometry. Okay. And so for these notes, these ones are kind of long since it's a review. So I'm gonna split them in 2 parts based on how I felt with the topics, how they fit better. Of course, at any time during these notes, you are free to take a break, go back and listen to something you've heard if you didn't quite understand it. But these 2 parts, it's one whole set of notes, but just split it into 2 parts to make it easier to understand. All right. So starting with subatomic particles, right, we have the proton, neutron, and electron. And when we write these out, just to save time and space, we're going to use this notation at the top up here. So proton is P with the positive, neutron is N with the 0, and electron is E with the minus. Of course, if you want to write out the whole word, go ahead. But these are the shorthand notations that I'll sometimes use. Okay, so protons are positively charged, and they are located in the nucleus. So remember, with an atom, we have the nucleus in the center, and then we have the electron shells around it. So protons are in the nucleus, and they have a relative mass of 1 AMU, atomic mass unit. The neutron is uncharged, it has a charge of 0. It is also in the nucleus, and it also has a mass of 1. Electrons are negatively charged. They are located in the electron shells, right? So those are these shells or the circles around the nucleus. And they have a mass of 0. Okay, those are the only 3 subatomic particles you'll need to know for AP chemistry. There are some smaller particles that these are made out of. This is still being researched. We are not going to talk about these at all, but if you're interested in that, you're free to look that up. Okay. So with atomic models, we started with Dalton. Dalton talked about how the atom is an indestructible ball. It's just a sphere. Think about like a marble or a bouncy ball. Thomson put some charges into there. So he had the plummeting model, where we said that the atom is a positively charged ball with negative charges inside of it. Rutherford took that and said that the positive was only right in the center, in the nucleus, but it's mostly empty space in the atom. He also kept the negative charged electrons around there. And then Bohr went off of Rutherford's model with the nucleus still being there with the protons and neutrons, but the electrons are now quantized, so they're on the specific energy level, right? So we have the first energy level, the second energy level, and so on and so forth. Some other important people to know, so we talked about Dalton. Dalton had 5 postulates. So with these postulates, his first one is that elements are made from atoms, right? This is true, we know this, we've talked about this. The second one's all atoms of a given element are identical. This one is not true. We'll talk about this here in a minute, but if you remember with isotopes, isotopes have different number of neutrons. It has a different mass. So this one is not true of his postulates. His third postulate is that atoms of a given element are different from those of different elements. Remember, we said that protons determine the type of element you have. So if an element has a different number of protons, it is of a different type of element, right? So carbon has 6 protons, nitrogen has 7 protons. They're different. The fourth one is atoms combine to form compounds. This is true. And the fifth one is atoms cannot be created or destroyed in chemical reactions, right? So we talked about the law of conservation of energy and mass, right? So if we have a reaction, the atoms cannot be created or destroyed, but they can be rearranged. We can move them around. Crookes looked at the cathode ray tube experiment, and he saw that there are negatively charged particles. So he looked at the electron, right? So the electron. J.J. Thomson also did cathode ray tube, and he talked about the mass to charge ratio of the electron. So this means that he looked at the electron being a mass of, it's relatively 0 to a -1 charge. Millikan did the oil drop experiment, and he also confirmed the charge of the electron being negative. Rutherford did the gold foil experiment, which looked at the protons and neutrons, he looked at the protons and found they are in the nucleus of the atom. Schrödinger talked about the wave nature of electrons, which we'll talk about later with the quantum numbers. And Chadwick discovered the neutron. So going into isotopes and average atomic mass, so this is the point where we're going to start talking about mass a little bit. So remember, isotopes have the same number of protons, so it's the same element, but a different number of neutrons, which changes its mass. So for example, if we have carbon-12 and carbon-13, carbon has 6 protons. It's number 6 on the periodic table, right? So it has 6 protons regardless of its mass. But because the masses are 12 and 13, we can determine the number of neutrons. For carbon-12, if it has mass of 12 and 6, so mass of 12 and 6 protons, 12 minus 6 means 6 neutrons. Carbon-13 has a mass of 13, still has 6 protons, 13 minus 6 is 7 neutrons. Okay, so remember, we have 2 ways to show these isotopes. We can have it how it is here in this, this example that I just talked about. So we have the element name followed by the mass. So remember, the mass is the protons plus neutrons. You can also have it how it's shown here in the image on the right, on the upper right, where so H is hydrogen, that's the element. The number on the top left is the mass, so it has a mass of 1. The number on top, or on the bottom left is atomic number. That's the same as the number at the top of the square on the periodic table. Right, so if you look at these hydrogens, they all have an atomic number, the number on the bottom left of 1, but the top left changes, the mass changes, which shows that it has a different number of neutrons. And you can also see that in the image on the top, if that helps you better. The red circles are the neutrons. You can see that the number of protons, the blue circle, stays the same, but the red circles, the neutrons, changes. That is an isotope. Okay, when we're talking about average atomic mass, so we calculate this by doing the mass multiplied by the percent abundance. Okay, so the percent abundance is how frequent this isotope occurs. And we're going to do this for each isotope that we have. Okay, so average atomic mass here at the bottom, it's the sum. So that symbol is the sum. You're going to add them up. The mass times the percent. And when we do percent, we want to change that to a decimal. Okay, so the reason we do this is because isotopes aren't even. They come at different frequencies. So if we look here on the right with magnesium, magnesium-24 has a percent abundance of 78.99%. Magnesium-25 has 10.00. Magnesium-26 has 11.01. So that means magnesium-24, if we just look in nature for magnesium, we'll find magnesium-24 78.99% of the time. Magnesium-25 only 10% of the time. So the average atomic mass is looking at the average of these. So to do that, you're going to take the percentage, change it to a decimal. So when we change to a decimal, you either divide, you're going to either divide by 100, or you move the decimal place over 2 times. So if we had 78.99, decimal moves 2 times, that becomes 0.7899. And you multiply that by the mass, which is given in the third column. So the decimal times the mass gives us this number here on the right. You're going to do that for each isotope. Remember that sum, that symbol we had at the beginning, means you're going to add them up. So if we add up those portions, our answer there is our average atomic mass. Okay. So our average atomic mass is also the number that's on the bottom of the squares of the periodic table. So if you're given percentages, if you're given the mass of an element and you're finding percentages, you can use a number on the periodic table as what the answer is going to be. Okay, so let's do some examples with this. Okay, I'm going to zoom in a little bit so I can write a little better. But you guys have these on your notes, so make sure you follow along. If you want to pause this and do it on your own first, you can if you feel confident. If not, you can just see what I do here and learn from this, and you'll have examples in your practices as well. Okay, so this first one, we have 99.3% of nitrogen 14 and 0.7% of nitrogen 15, right? So we are calculating the average atomic mass. Remember that the equation was, so the average atomic mass is equal to the sum of the mass times our percentage for each isotope. So for this one, we have two isotopes. We have nitrogen 14 and we have nitrogen 15. So for nitrogen 14, our mass is 14. Our percentage, remember, changed to a decimal, is going to be 0.993. Okay. Then we're going to do plus our second isotope. So mass of 15 for nitrogen 15 times the percentage, if we divide by 100, is 0.007. And then we're going to solve for it. We're going to put an equal sign. So if we do this math, we do 14 times 0.993 plus 15 times 0.007, we get 14.007 AMU, atomic mass units. Okay. Remember, whenever you're doing any calculations, whenever you have numbers, you almost always want to have units with them. Some numbers we won't associate units with. We'll get to that later in the year. But whenever you have numbers, you want to have units. Okay. For our second example, we have three isotopes. We have oxygen 16, oxygen 17, and oxygen 18. Okay, so remember, we're going to do the mass. So first one, oxygen 16 has a mass of 16 times the percentage, change to a decimal, is 0.99762. Okay, then we're going to add our second isotope. So oxygen 17 times change of percentage to a decimal is 0.00038 plus our third isotope has a mass of 18, change the percentage to a decimal, 0.200. And if we do the math here, we should get 16.00438, and the units here are atomic mass units, AMU. Okay. For this third one, we're doing the same thing. We have three isotopes. We have silicon 28, silicon 29, and silicon 30. But the data here is just shown in a table instead of given as in a sentence. Okay. So for these ones, when we're using the mass, they gave us here on the right some more precise mass numbers. We have decimals there. So we're going to use those mass numbers instead. So we're going to change our percentages to decimals, right? So 0.92230. Sorry, let me make that a little clearer. 92230, 0.04680, 03090. Okay, so we're going to do our percentage times our mass. Right, so multiply these across. So for the first one, 0.92230 times 27.977, we get 25.803. And whenever you're doing math, so we're doing calculations as intermediate steps before we get the final product, these intermediate steps keep your decimals. Don't round them at all yet, okay? You can round them slightly, but don't round them too much. Our second one, we have 0.04680 times 28.976. You get 1.356. The third one is 0.03090 times 29.974. And for this one, we get 0.9262. Okay, and remember from here, we're going to add these up. We found the relative abundance for each isotope. So now we're going to add them up to find the total percent abundance, the average atomic mass, right? And if you add them together, we should get 28.085 AMU. All right, so that's how we're going to find the percent abundance, the average atomic mass if you're given the masses. But like I said, sometimes you're not given the percentages. You're given the masses, and you're given the final average mass from the periodic table, and you need to find the percent abundances. Okay. Remember, for percent abundance, we're looking at a percentage. Percentages add up to 100. So if we substitute the percentages with X for one isotope and 1 minus X for the other one, those will add up to 100 in the end, right? So for X, let's say, is 20. 1 minus X, so 20%, remember, is 0.20. 1 minus X will be 0.80, or 80%. Right, so those 20% plus 80% is 100%. So we can use this to do some algebra. We set our isotopes equal so that the percentages so that it adds up to 100% at the end. So let me zoom in on our practice question. So the first one, we have calculated the percent abundance of each isotope of nitrogen. Right, so we have nitrogen. We can look at our periodic table, and we know that nitrogen, I believe, is 14.007. Just make sure so I don't use the wrong number. Yeah, so on the periodic table that you're given from AP, it's 14.01. So we'll use the AP number. And we have two isotopes. So our first isotope, nitrogen 14, has a mass of 14.00307. Our second one, nitrogen 15, is 15.000108. Right, so that's a lot of numbers. But that's the number it gave us, a lot of decimals. We're going to use all those decimals when we do our math. So our first isotope, we're going to do the same formula. We have our mass, 14.00307. And then for the percentage, remember our first percent, we're going to use X. Then we're going to add our second isotope. So our 15.000108. And then the percentage here is 1 minus X. Be careful that you don't do X minus 1, because that will not get you the correct answer. That'll mess you up. And remember, this is equal to our number on the periodic table, which is 14.01. Okay, and then here you just do some algebra. So we have 14.00307X plus 15.000108 when we do that times the 1. And we're also going to do it times the negative X. So minus 15.000108X is equal to 14.01. Right, so now we're going to combine like terms. We have two numbers that have an X in them. So if we combine those, we get negative 997.038 X, and then we're adding the number that does not have any variables on it. It does not have any like terms, equals to 14.01. Okay, I'm going to move down here just so I have some more room. Okay. So if we want to get our X on our own, we're going to subtract the number without the x, because it has a like term on the other side. So if we subtract that over, so we're going to do minus 15.000108 on both sides. On the left, we're left with the x term, so 997,038x. And then if we subtracted it to the other side, we get negative 0.993108. Okay, and then to get x alone, we're going to divide by the number it's with, the 0.997038, taking the negative with it. Do that on both sides. And we get x equals 0.996. Right, so what does that mean? Let's look back at our question. We're looking for percent abundances for each of these isotopes. So if x is 0.996, that means our first isotope, nitrogen 14, has a percent abundance of, remember we said that was x in our equation. So it is just 0.996, which we can also write as 99.6%. Our second isotope, nitrogen 15, it's 1 minus 6. So 1 minus 0.996, minus 0.996 gives us 0.004. Right, so as a percentage, that becomes 0.4%. So those are our percent abundances for two isotopes. Okay, going on to the second question. Let me erase this down here so we have some room. We're looking at strontium. We have, again, two isotopes, strontium-86 and a strontium-88. And it gives us our average atomic mass in this question here. So I want you guys to go ahead and do this, right? Set it up with the mass. So 86 times the percentage, figure out what goes in that parentheses, plus our second isotope times the percentage, figure out what goes in there, is equal to 87.62. I want you to go ahead and work this out. And you should get that strontium-86 has a percentage of 16%, and strontium-88 has a percentage of 84%. Okay, so work through that. If you need help, let me know and I'll help you. We'll have time in class to work on this, or you can come into tutoring, okay? So that is it for average atomic mass. There's two ways you'll be asked to calculate it. Okay, so one where you have the masses and the percentages, you're looking for the average atomic mass. The second one where you don't have the percentages and you're looking for the percent abundance. Okay. So when we're looking at mass percent, okay, so mass percent, we're looking at the element in a compound. To do this, we're going to follow a few steps that are listed here. We're going to find the mass of each element using the molar mass from the periodic table, find the total molar mass of the compound, and divide the molar mass of the element by the molar mass of the compound, and then multiply by 100 to get a percentage. Right, so if we're looking for each element, this first example here, we have calcium chloride, CaCl2. So we're going to split this up into two elements because we're looking for each element. So we have calcium and we have chlorine. Okay. So for calcium, the mass on the periodic table is 40.078. For chlorine, it's 35.453. But don't forget, in our compound, we had two of them. So we're going to multiply this by 2. We get 70.906. Okay, so that's the first step. The first step, we found the mass of the element from the periodic table. Our step 2, we're going to find the total molar mass from the compound. So if we add these two together, so 40.078 plus the 70.906, we get 110.984. All right. Our third step, we said we're going to divide the molar mass of the element by the molar mass of the compound. So we're going to do the black number divided by the blue number for each of them. So for calcium, we're going to do 40.078 divided by 110.984. For chlorine, we do 70.906 divided by 110.984. Right, so the mass of the compound, the number on the bottom, is the same for both of them. The mass of the element depends on the element you're looking at, which part of the compound, calcium or the chlorine. Right? If we do this division, for calcium, we get 36.11%. For chlorine, we get 63.89%. Okay, so remember, whenever you do this, you'll get a decimal first. Let me show that. So for calcium, you'd get the 0.3611, and this you would change to a percentage to be 36.11%, because we're looking for the mass percent. Okay, so for chlorine, 0.6389, change to a percentage is 63.89%. Okay. The second one is the same thing. I'm going to let you do this. So in this compound here, we have sodium, sulfur, and oxygen. Be careful with your numbers. You have 2 sodiums, 1 sulfur, and 4 oxygens. But you're going to do the same thing here. So you're going to look at the mass of the element times how many you have. Then you're going to find the molar mass of the whole compound together. And you're going to divide the element by the compound. So same thing we did for the first question above. Okay, so for this one here, for sodium, you should get 41.78%. Sulfur, you'd get 29.14%. And for oxygen, you should get 29.08%. And remember, with percent composition, we're looking at the percentage of the element for the whole compound. So a good way to know when you're working through this, if you did something, or if it looks right, is these numbers should add up to 100%. Because it's everything that makes up the compound. Right. We're going to do the third question on this slide together, because it's a little bit more thinking, right? So we can use mass percent to determine if something has been contaminated. So the question says, a student believes that a sample of solid rubidium chloride may be contaminated with cesium chloride. Knowing that pure rubidium chloride contains 29% chlorine by mass, the student performs the experiment to determine the mass percent of chlorine in the sample of rubidium chloride. What should happen to the percentage of mass of chlorine if it's contaminated with cesium chloride? Okay, so if we're looking at this, we have 2 things. We have rubidium chloride and cesium chloride. With rubidium chloride, it has a mass percent of chlorine of 29%. So with RbCl, the Cl percent is 29, right? If it's contaminated with cesium, what would happen? So if we look at the cation, so we have either rubidium or we'd have cesium with the chlorine. Rubidium on the periodic table has a mass of 85.47. Cesium has a mass of 132.91. So cesium is a lot bigger than rubidium. So if cesium was in this sample, if it was contaminated with cesium, cesium would take a bigger percentage of the mass, which means that cesium would go up and chlorine would go down, right? So what would happen to the percent mass of chlorine? This number would be less than 29% if cesium was in there. If we went the other way, if we added, say, potassium chloride, KCl, potassium has a mass of 39.10, right? So if it's smaller, that means the cation, or potassium here, would have a smaller mass percent, which means that that goes down and the chlorine goes up. Okay? So oftentimes with AP questions, it's sometimes well-asked questions, like what we had on the left, where you are just looking, you're doing the math, you're finding a percentage. But sometimes you also have questions like those on the right, which takes it a step further, and you'll have to use some critical thinking skills. Okay, so we'll be practicing that in class. All right, mass spectrometry. This is one of our new topics in this unit. So mass spectrometry, this is a technique that separates atoms based on the isotope weight. Okay, so this is a large instrument that's used like in research or in industry, and it shows us a graph with the isotopes. Okay, so the y-axis is our percent abundance. The x-axis is the atomic mass. Okay, so that's what we've been talking about this whole time. Nothing's new. It's just going to be displayed on a graph visual. All right, so if we look at the graph here on the left, it's not labeled on the bottom, but remember the bottom was the atomic mass in AMU, and then the left is our percentage, right? So whatever element this is, we know that at about 19, so this first line here, at about 19 atomic AMU, that's at about 90%. Our second line at about 20, or sorry, 20, the blue one would be 19.9 something. The red one here would be about 20.9. That one is almost negligible, right? That's about 1 or 2%. And our last isotope, our last bar, at almost 22, that one would be at about 10%. Okay, so that's how you're going to read these graphs. When you're looking at graphs, whether it's mass spectrometry or whatever else, make sure you look at the axes first, because this one is started from 19 on the left and it went higher as you go to the right. Sometimes graphs will go the other way. It might have 19 on the right and it goes higher as you go to the left. So just make sure you're reading your axes, know what the graph is saying before you answer the question. Okay. But with these graphs, you could have something like this. So this is a question that says that gives you a mass spectrometry graph, and it says the elements of iodine and tellurium, INTE, have similar average atomic masses. The sample was believed to be a mixture of INTE, was run through a mass spectrometer, resulting in the data above. All the following statements are true. Okay, which of the following could be the best basis for concluding that the sample is pure tellurium? So all these statements are true. They're not lying here, right? They're giving you facts about both iodine and tellurium. But it's asking which one supports that this graph that it gives us is just for pure tellurium, right? So for A, tellurium forms ions with a -2 charge, whereas iodine forms ions with a -1 charge. So although that's true, this graph that we have, the mass spectrometry, we aren't looking at charges. We're looking at percentages, and we're looking at mass. So although this is true, it has nothing to do with our graph. B says that tellurium is more abundant than I in the universe. And although that's true, if we don't have the right abundances, or even if it's true, this isotopes, this graph is just looking at an 100% abundance. It's looking at a single element. So this is true. We're not comparing elements in this graph. For C, iodine consists of only one naturally occurring isotope at 74 neutrons, whereas tellurium has more than one isotope. Okay, so this could be supportive of this graph because this graph has more than one bar, right? It has 1, 2, 3, 4, 5, 6, 7 bars. That means 7 isotopes. So that supports that tellurium has more than one isotope, but saying that iodine only has one naturally occurring isotope would mean that it would only have 1 bar, not 7. Okay, so this one might be true. We're going to leave it. And then D, iodine has higher first ionization energy than tellurium does. Even if that's true, again, it does not have anything to do with this graph, so that's not right. So we know here our correct answer is going to be C. Okay, so when you're going through these questions, make sure you use test-taking strategies, use process of elimination, and go one answer choice at a time. Eliminate what you know is wrong, leave what you think is a possibility, and look at all the answer choices first before making your choice. Okay? So for mass spectrometry, you can have a question like this where it gives you a graph and it asks you about the graph. Or you can do something like we've done before and you find the percentages and then you graph it yourself. Okay, so make sure you're comfortable with these graphs. Right. For empirical and molecular formulas, remember when we talk about empirical formula, this is the simplest form. So this has the lowest common denominator for our subscripts in the compound. Okay. To find this, we're going to convert the percentages to grams. We're going to convert the grams to moles, divide all the moles by the atom with the lowest number, and then multiply or round the ratios until all our numbers are whole numbers. Okay. Remember, if we multiply one element, we have to multiply all of them. So let's do these steps with these questions on the right. Okay. So for 7.91% phosphorus and 92.81% bromine. So we have percentages, we need to change it to grams. The easy way to do with grams is assume you have 100 grams total sample. 7.91% of that is 7.91 grams for phosphorus. 92% of that is 92.81 grams. Okay. Step 2, right, if we go back here on the right or on the left, step 2 is we're going to convert our grams to moles. Remember, to go from grams to moles, you're going to divide by the molar mass. The molar mass for phosphorus on your periodic table, number 15, is 30.97. And the molar mass for bromine, number 35 on your periodic table, is 79.90. Okay. If we do that division, we get 0.2554 for phosphorus and 1.1615 for bromine. Okay. The next step is to divide the moles, because now we're in moles, by the atom with the lowest number. So our lowest number here is going to be the 0.2554. So we're going to divide both our numbers by 0.2554. Okay. So if we do that for the first one, for phosphorus, a number divided by itself is 1. For the bromine, we get 4.5. Okay. And then for our last step, we have multiply or round your ratios until all numbers are whole numbers. So when talking about rounding, we don't want to get too crazy with it. If we're at like 4.9 or higher, or if we're at 4.1 or lower, you can round that. But this one's 4.5. We don't want to round this. So to get to a 0.5 to a whole number, we need to multiply by 2. Remember, if we do that to 1, we need to do that to both. So for phosphorus, 1 times 2 is 2. For bromine, 4.5 times 2 is 9. So our ratio for phosphorus to bromine, it's a 2 to 9 ratio. So our empirical formula is P2Br9. Okay. I want you to do the same thing with the next two. So for the second one, we have copper and we have oxygen. Okay. And you should get the formula of 2 coppers to 1 oxygen. And for the third one, we have 3 elements, carbon, hydrogen, oxygen. Okay. You're going to do the exact same thing, just with 3 elements. Nothing's going to be different. Okay. And for this one, you should get C3H6O2. Okay. So looking at this question down here, going to molecular formula, right? So for molecular formula, this is the actual formula. It takes that empirical formula and it has a bigger mass. It's a multiplied variant of it. So we're going to have our empirical formula's molar mass. That's the first step. We're going to divide the molar mass of the compound that was given by the empirical formula's molar mass to find the ratio between them. And then after that, we're going to multiply the subscripts in the empirical formula by the ratio that is determined. Okay, so in this question here, we have our formula of CH2O, and we have our final compound has a mass of 180. Okay, so first step was find the molar mass of a compound that was given. So for CH2O, 1 carbon, 2 hydrogens, 1 oxygen, right? So that's 12.011 for the carbon, 1.008 times 2, because we have 2 of those for the hydrogen, and then 15.999 for the oxygen. We get a mass here of 30.026. Okay. Our next step was we're going to divide the molar mass of the compound that was given by the empirical formula's mass. So the given was the 180, that's what we had here, divided by the mass we just got, the 30.026. That division gives us a ratio of 6. So that's our ratio. The final step is we're going to take the compound we had, the CH2O, and multiply all the subscripts by 6. So C becomes 6, H 12, and then O 6. All right. That's all we're going to talk about with mass for now. We're going to move on to electrons. And this is going to be the last little switch for this part. We're going to talk about electrons and the periodic trends. And then that'll be it for the first part. We'll take a little break and we'll go to the second part. Okay. So with electrons, we have the Bohr model. So electrons are quantized onto energy levels, right? We have different levels. We have 3 rules when we talk about electron configuration. The Aufbau principle says that electrons are starting at the lowest energy level first. Pauli exclusion principle is that electrons cannot have the same 4 quantum numbers. They have to be different. Okay, so that means that if they're in the same orbital, they have opposite spin. And then the Hund's rule says that electrons will occupy each orbital within a subshell individually before pairing up. Okay, so with electron configuration, we're looking at the coefficient being the period, the letter being the subshell, and then the exponent is the number of electrons, right? And when we talk about electron configuration, we're talking about that like 1s2, 2s2, 2p6, etc. that we've done before. Okay, this down here we'll talk about here in a minute. This is called the orbital diagram. This is going to be a second new thing in this unit. All right, but so for electron configuration, right? So remember, we have numbers and letters from the letters that talk about subshells, the S, P, D, and F. Remember that those are regions of the periodic table. The first 2 columns are the S. The green on the right area here is your P. The yellow in the center is your D region. Okay. The lanthanide and actinides here is the 2 that are detached on the bottom. Those are your F block. Okay. And remember, we follow it linearly. So we go across a row first. When we reach the end of the row, we go to the next row. Okay, so if that helps you, you're free to use that. Where'd I have it? On this slide here, you might have seen this image from from when you took chemistry. If following this diagram helps you as well, so just follow the arrow and do the domains as they go through the arrow, you can follow that as well. Okay, but let's look up here real quick. So for nitrogen, right, if we follow the periodic table, let me zoom in a little. Nitrogen is right here. Let me just color that in. That's where we're trying to go. So remember, we start at the beginning. We start with the 1s, and we go 1, 2 squares over. So 1 is for the first row. S is because we're in that purple region. We're in those first 2 columns, and the 2 on top is because we're in 2 boxes. Okay, and a little note here, the helium is a green box. This should actually be a purple box. It's part of the S region. Okay, the second one, we have 2s2, right? Because we're in the second row. We're still in the purple, we're still in the S, and we go 2 boxes again. After that, we don't go down yet because we can still go across. There's more boxes in the row, right? So here we're still in row 2. So that's why we have a 2 in front. We're now in the green. So the green is our P. So we have 2P and we go 1, 2, 3 boxes. That's why we have a 3 on top. Okay, so that's the gist of doing electron configuration. When you're doing orbital diagram, so orbital diagrams show the same thing in a more visual representation. So we have boxes and arrows here. The arrows are the electrons and the boxes are those subshells, right? So we started with nitrogen with 1s2. So our first box is going to be 1s. We have 2 electrons, so we draw the 2 electrons as arrows, the up arrow and the down arrow. Remember, we draw up arrows first, then if we have to double up, the other one's an opposite spin, so that's why it's a down arrow. Same thing with 2s2. We have the 2s has 2 electrons, so 1 up, 1 down. With 2p, remember p can hold 6 electrons. So to hold 6 electrons, we need 3 boxes. Since we only have 3 electrons here, we're going to fill each one up first with 1 before we go back and double up. So if we have 3, each one is just going to have an individual 1. If for oxygen, we'd have a 4 there, our 4th arrow goes back to the first box of the 2p and it goes as a down arrow. Okay. So this orbital diagram is going to be the new piece here. So make sure to practice it. It's the same thing, just in a different representation, more visual. Okay. So for ions, if you have an ion that either gained or lost an electron, you're going to show that in the electron configuration. So for a cation, we're losing an electron. So for sodium, for example, right, that 3s1 at the end, that last electron is going to be lost. And you can see here that 3s1 is no longer there. We got rid of it because we lost 1 electron. Okay. With anions, we add an electron. So for chlorine, that 3p5, we add an electron that becomes 3p6. It gains 1. Okay. And ions can make atoms isoelectronic, right? So isoelectronic just means that they share the same electron structure and number of valence electrons as another element. So in this case here, sodium became isoelectronic with neon. So 1s2, 2s2, 2p6. That's where neon lands on the periodic table. Chlorine is with argon. Okay, that's all that word means. Okay. For transition middles, they're a little bit odd, just overall. We don't do a lot with them, but with electron configuration, because they're in the d subshell, when you remove or gain electrons, they're actually going to come from the s subshell because it's at a higher energy level, right? So you want to get rid of the higher energy level first so it could be more stable. Okay. So for example, with zinc here, this first example, we have 4s2 3d10. If it becomes a cation, it gains a positive 2 charge. Those 2 electrons that it loses are going to be from the 4s. You can see that's no longer there. All right. And then also remember, with electron configurations, you can use what we say as the abbreviated notation, which is you start at the most recent noble gas and you go from there, right? So remember, let's take sodium. We had 1s2, 2s2, 2p6, 3s1. We can start at the most recent noble gas. So if we go to our table up here, sodium is here. The most recent noble gas is on the row before, all the way at the very end, which is neon. So we're going to start at neon. And that's essentially substituting all of that. That's what neon is. So we continue after it. So neon and then 3s1. Okay, so you can use either notation when it comes to work in my class unless a question specifically asks. But some questions on the practice you'll have and on the AP test will specifically say, write the electron configuration for the valence electrons, just the ones on the outer shell, right? So that'll be the one with the highest number in front. So you'll look for sodium, we'll only write the 3s1. Sometimes it'll also say write the complete electron configuration. So that'll be the whole thing, not the abbreviated. So be careful with the wording of the question. Okay. So I want you guys to practice with these ones. Okay, so oxygen, lithium, and iron. Go ahead and pause the video if you need to, but I want you to practice first. I'm going to write the answers on here for you, though, so that you can see if you got them correct. So for oxygen, you should get 1s2, 2s2, 2p4. You can also write this as helium for the abbreviated notation. Okay. So it says full electron configuration, that's the abbreviated notation, and then we're also doing the orbital diagram. So remember, orbital diagram is the same thing, but with the boxes. So we start with the 1s, we have 2 in there, 1 up, 1 down. Then we go to the 2s, again we have 2, 1 up, 1 down. Then go into the 2p, we need 3 boxes here. We have 4 electrons, right? So we need 4 arrows. Start with 1 in each box, then go back and double up in the opposite direction. That's our orbital diagram. Okay. With lithium, with the positive 1 charge, so we lost an electron, that's just 1s2. Okay. The abbreviated notation, because this is the notation for helium, there is no abbreviated notation. It's just that. And then for the orbital diagram, we have the 1s and we have 2 electrons in there. Okay. And then the last one for iron with a 2+ charge. Okay. This one is sorry, give me this one should be a 3+ charge. It's a mistype on here, sorry. So I'll fix that on the notes, but that should be a 3+ charge on there. But the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Okay, so you'll notice here, I got this whatever originally without the charge. This part would have been the same. Then we would have had the 4s2, 3d6. But remember, with a charge, you take away from the s first because the higher energy level has a higher number in front. So we got rid of those 2 first, and the third one came from that d. Okay, so that's where I got those numbers from. The abbreviated is argon, 3d5. And then for the orbital notation, right, we're going to start with the 1s. We have 2 electrons there. 2s, we have 2 electrons. 2p, we have 6 electrons. So 1 in each first before we go back and double up. 3s, we have 2 electrons. 3p, we have 6 electrons. So if you know you have a full thing, you can do them as you go, but remember, 1 in each first and double up after. I'm going to show the 4s box because it goes here, the orbital, but I don't have any electrons there, so I'm going to leave it empty. And then for 3d5, remember D can hold 10 electrons, so I need 5 boxes. It's going to get a little cramped. Okay, so that's my 3D. And I said I had 5 electrons. So I'm going to put 1 going up in each box. 1, 2, 3, 4, 5. And I don't need to go back and double up. So I stop there. Okay. So remember, try these. Make sure you know how to do them. Make sure you know how to write all 3 formats. If you need help with this, let me know. The orbital diagram is new to you, remember? So if you struggle with that, that's okay. We can work on getting better with that. Okay. So for this question here, which of the following represents the ground state electron configuration for the Mn3+ ion? Okay, so Mn is right here in the D. and we have a 3 plus. So we should have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5. But remember, we have a 3 plus ion. So we're going to get rid of our 4s first, and then change the 3d to a 4. Get rid of one of those two. Okay, so which one matches that? We have 1s2, 2s2, 2p6, 3s2, 3p6, and the only one with 3d4 is A. So that's our correct answer. All right. We'll do a little bit more with electron configuration and unit 1, where we talk about it with excitation and relaxation, but you don't have to worry about that yet. Okay. The last thing for this part 1, is going to be our periodic table. Okay. So the periodic table, remember, there's a lot of things to label here. So starting with our charges, starting with what things are. Our periodic table in the center here, we have each square has different numbers in it. This one has a lot more numbers than what you'll typically see. What you'll normally see is what's circled here. So you'll have the chemical symbol, so it's right in the center. That just tells you what element it is. The name also tells you the element. On this one here, it's at the top. This will normally be at the bottom for you. This is the atomic weight. Okay. And then this number at the top right here, this would normally be at the top. This is your atomic number. It's how many protons you have. Okay. And remember, with periodic tables, our groups, so these are up and down, they're called the groups, the columns. That tells you how many valence electrons there are. The rows, the left and right, are called periods. That tells you the number of electron shells. So what I mean by that is, so here, you see that 2 there? That means beryllium. So if I draw beryllium out, you have the nucleus. You have 1, 2, 3, let me draw this somewhere better, 3, 4 electrons for beryllium. Okay, so valence electrons is the outermost. So on our outermost shell, this one right here, we had 1, 2 electrons. So it's in column 2, it has 2 valence electrons. For the shells, that's how many circles or how many rings it has around it. We had 1, 2 rings. That's why it's in group 2. Okay, so that's what those numbers tell you. All right. When we're looking at the periodic table also, remember we have charges for when they become ions. So group 1 becomes a +1, group 2 is +2. And then transition metals, we don't assign it because it can have more than one. So if you see here with iron, this is a transition metal. This has quite a few oxidation states or charges. Okay, so we don't assign them for transition metals. But coming over here for this group with boron, that's +3. Carbon's group is plus or -4, so it can go either way. And then after that, it descends. So nitrogen's is -3. Oxygen is -2, the halogen's -1, noble gases is 0. So charge is 0 here. That means it's not reactive. It's not going to react with something. It's not going to make a compound. Okay. Make sure you also know that, so on your periodic tables, you normally have a solid line, a staircase going down. To the left of it, those are your metals. To the right are your non-metals. The exception here is hydrogen. Hydrogen is a non-metal. Okay, but make sure you know your metals and nonmetals. That comes into play for covalent and ionic bonding. You should also know the names of each group, right? So our group 1 is our alkali metals. Group 2 is alkaline earth metals. In the center, we have our transition metals. At the staircase, we have our metalloids because they're between the metals and nonmetals. Our halogens is group 17. Group 18 is our noble gases. And then at the very bottom, we have our lanthanide and actinide series. You should also So on the bottom left here, the circle, the S, P, D, and F regions for the electron configuration. And then on the bottom right, make sure you know that isotope notation or the element notation to understand the mass number and the number of protons. And then if there's a number on the top right, that's the charge of it. Okay, so make sure we understand those. You should have already gotten a periodic table, so if you need to label this on a periodic table so you have it to reference, you're free to do so. But note that you will not be able to use that as a reference on tests, so make sure we know this. Okay, talking about periodic trends. So atomic radius is the radius or the size of the atom. So cesium is typically the biggest. As you go to the bottom and as you go to the left, it gets bigger. So that means as you go up, these elements will get smaller and smaller. Same thing as you go from left to right. They get smaller and smaller. Okay. For ionization energy, that's the energy to remove an electron. Helium, it's the opposite of cesium, so it's very small. So that means it's pulling really tight on its electrons. It's hard to remove them. Cesium is quite large. So on the bottom left here, if it's a larger element, it's easier to remove those electrons. And the last trend is electronegativity. It also goes the same direction as ionization energy. And this is the attractive force on the outer electrons. So here we have fluorine as being the highest. So fluorine has the highest pull on the outer electrons. The bottom left area here would have the lowest pull on those outer electrons. Okay, so make sure you know these periodic trends. And the next unit, unit 1, we'll talk about Coulomb's law, and we'll talk about how that affects each one of these. Okay, so just a visual for atomic radius, you can see you have the biggest atoms down on the bottom left, the smallest up on the top right. And then with ionization energy, right, you'll see that the noble gases always have the highest for the period, not just in general, but just for the periods, right? So this is hydrogen and helium. This goes lithium, beryllium, and so on and so forth for the period 2. Okay, so let me write these down for you. So this is period 1, period 2, 3, 4, 5, and so on and so forth. You'll see that as the period goes to the right, it goes up. And then as you go to the next period, it goes down. It drops down significantly. Okay, so make sure you understand periodic trends with ionization energy. Okay. This is another chart that shows the same thing. Okay, so looking at ionization energies, these I1, I2, that's the number of ionization energies. So I1 is removing 1 electron. I2 is removing the second electron. I3 is removing the third electron, right? So for sodium has, I'm just going to draw the valence shell. It only has 1 electron in the valence shell. Magnesium has 2 electrons, right? So that's why when you look at these ionization energies, I1 is low for both of them. But I2, you'll notice that it's significantly higher for sodium than it is for magnesium, because you're not removing a valence shell electron, you're moving one of the outer ones. Because I1, this removes 1, and now that valence shell is gone, so you have to remove something from the inside. Same thing for magnesium with I3 here, right? It jumps up quite significantly because you've already removed 2 of them. The third one has to come from an inner shell. All right, that is it for Unit 0, Part 1. I'll make a second video for Part 2. Make sure you watch that to complete the notes. And remember, if you have any questions about these, I hope you wrote them down as you were going along and you're doing those practices. We can talk about them in class or during tutoring.